Swayam Prabha. Digital India. Educated India.
Today we will start with a new topic, thin film dynamics. Now this topic has a bit of relationship with the lubrication theory that we had learnt earlier. In the lubrication theory that we had learned, we discussed about a narrow gap in which there is a fluid driven by some force, and the length scales could be separated in such a way that the gap height is much smaller as compared to the axial length scale, and the gap height could be varying with position, and however the variation in the gap height is such that the gap height by the length scale, the average or the length scale representing the gap height divided by the axial length scale, that remains small under all circumstances. So that was the condition that we considered, and thin film dynamics, as we see here, also deals with flows of very thin films whose height is very much smaller than the length. But the difference between the thin film flows and the kind of situations that we addressed through lubrication theory earlier is that there both the boundaries were rigid. Now here there is a free surface that we are talking about, which is the surface, the interface between the liquid and say another medium, which may be a gaseous medium. So this thin film dynamics is essentially talking about free surface flows where thin liquid films are formed, and of course we can use lubrication theory in this context as well, but the context in which we used lubrication theory earlier, the difference between that and this is that there we talked about a rigid boundary at the top, and here we will be considering a free thin film surface at the top. So one can easily infer that, I mean, except for this difference, but this is a big difference, and we will see that what is the implication of this big difference. But except for this big difference, one can easily infer that flow of fluid in a thin film will have good resemblances with lubrication flows, that is flow in slide, for example flow through slider bearings for example. In thin film flows also, the velocity in one direction dominates over the other, that is there is a dominant direction of flow. That is, if you recall that in lubrication theory we had the velocity scales UC and VC along x and y, where UC is much greater than VC. So here also the same thing will hold true, that means although there are the possibilities of having both components of velocity, but one component of velocity dominates significantly over the other. But there are some subtle differences between thin film dynamics and lubrication theory. In lubrication, typically in lubrication, I mean it is, we should not say that the difference between thin film dynamics and lubrication theory, but better to say thin film dynamics and situations pertaining to lubrication, because lubrication theory is a theory which can be used even in thin film dynamics, just the boundary conditions change. But typically in lubrication the flow is bounded on both sides by solid walls, therefore at both the walls the fluid satisfies the no slip boundary condition. In lubrication theory usually height of the fluid or channel is known as a function of time or space. In thin film dynamics one of the surfaces is usually a free surface, as we have pointed out, therefore instead of no slip boundary condition the fluid satisfies the no shear boundary condition. We discussed about this boundary condition earlier, and we will see that how that we can fit that in the context of lubrication theory. Apart from this, the film height is in general not known. This is also a very important thing, that like when we are talking about say lubrication in say slided bearings, we know the height of the confinement, it is already given, but in thin films, for example, let us say droplet spreading on a substrate. So there, if you consider the height of the droplet being a function of time, that evolves with position and time in such a way which is not known a priori. So this is an important challenge in the lubrication in the thin film dynamics. Therefore, one has to look into additional boundary conditions, and these additional boundary conditions we will discuss in great details, which are known as the kinematic boundary condition and normal stress boundary condition. Now in what follows, we will discuss the thin film dynamics in much the same way as we did for the lubrication theory. Therefore, some algebra which we worked out in details for the lubrication theory, we will omit detailed discussions, and we have since we have already done those discussions in the lubrication theory, and we will straight away use the expressions, but wherever possible and wherever the algebra is simple enough, I will try to derive that for your recapitulation. Now to understand the thin film theory, we will start with the very special case of the thin film theory when the film surface is flat. Okay. So let us try to consider a situation. Let us say there is an inclined plane making an angle theta with the horizontal, and there is a thin liquid film on the top of it. We can for simple